Welcome to the deep dive. Today, we're going to unpack something pretty special.
All right.
A paper that threw open the doors to the world of deep learning.
Hmm.
It's called ImageNet Classification with Deep Convolutional Neural Networks. But most folks just call it AlexNet after the lead author.
It really is a landmark paper. It wasn't just about the technical stuff. It was
Yeah,
like
right.
a proof of concept for the whole field. People saw the results and suddenly thought, okay, this deep learning thing could be seriously powerful.
Yeah, it seems like it was a real turning point.
Yeah.
But for those of us who aren't, machine learning experts,
Here.
let's back up a bit. What was the landscape like before AlexNet came along?
Think of it like this. Before AlexNet, the machine learning world was working with smaller data sets, simpler models, and they were bumping up against some pretty fundamental challenges, like overfitting, where a model basically memorizes the data it's trained on but can't generalize to new information.
So like studying for a test by just memorizing the practice questions,
Yeah.
but then blanking out when you see the real exam.
Exactly.
Yeah.
Then along comes ImageNet, this massive data set of millions of labeled images.
Yeah.
It was like opening up this huge library of visual information. But the problem was, how do you build a model that can actually learn from a data set of that scale?
And that's where AlexNet swoops in, right?
Right. AlexNet was this deep convolutional neural network that just crushed the competition in the 2010 ImageNet competition. I'm talking a top 5 error rate of 17%.
Wow.
To put that in perspective, the previous best was around 25 to 28%. So this was a huge jump in accuracy.
Okay, so a lower error rate means the model is doing a better job of identifying what's in the images.
Yeah.
But can you break down what that 17% actually represents?
Sure. Imagine you show the model a picture of a cat
Okay.
and you ask it to guess what it is.
Yeah.
With a 17% top 5 error rate, it means that 17% of the time cat wouldn't even be in the model's top 5 guesses. So achieving 17% was a major breakthrough.
Got it. So it seems like AlexNet didn't just win a competition.
Right.
It was really a demonstration of what deep learning could achieve with a massive data set.
Exactly.
But what was it about AlexNet, about its design,
Right.
that made it so successful?
Well, it all comes down to its architecture, the way it's structured.
Yeah?
It had 8 layers that were actually learning from the data. 5 of those were convolutional layers,
Okay.
which are designed to pick out features from images, things like edges, textures, shapes.
Yeah.
Then there were 3 fully connected layers.
Got it.
And those are the ones that actually take those features and make a decision about what's in the image.
Okay, I definitely want to dig into those different layers a bit more.
Sure.
Because it sounds like that's where a lot of the magic happens. Can we start with those convolutional layers? What makes them so special?
Think of them like a set of filters that are scanning over the image. Each filter is looking for a particular feature.
Okay.
And as they scan, they learn to recognize that feature no matter where it shows up in the image.
Right.
That ability to learn those features is really what makes convolutional layers so powerful for image recognition. So it's not just memorizing specific images, it's more like learning the fundamental building blocks of those images.
Exactly. And that's key for generalization because it allows the model to recognize objects it's never seen before,
Right.
as long as it understands the underlying patterns that make up those objects.
Fascinating.
Yeah.
So we've got these convolutional layers finding those features,
Yeah.
and then the fully connected layers use that information to actually classify the image.
Right.
What else is going on in this AlexNet architecture that we need to understand?
Well, there were a couple of other things they did that were pretty innovative at the time. One was using something called ReLU, or rectified linear unit, as their activation function.
ReLU.
Now, the activation function basically determines whether a neuron fires or not based on its input.
Okay.
ReLUs are a lot faster for training because they avoid a problem called saturation that slowed down previous activation functions.
So using ReLUs was kind of like adding a turbocharger to the whole training process.
Exactly. They were able to speed things up significantly, which was critical when you're working with a network as large as AlexNet and a data set as huge as ImageNet. Another key innovation was using 2 GPUs.
2 GPUs.
Back then, a single GPU just didn't have enough memory to handle a model as big as AlexNet,
Oh,
so they split the workload across 2 GPUs.
divide and conquer.
Yeah,
Like it. But how does that work? Wouldn't that just create more problems?
could have.
Yeah.
But they designed the communication between the GPUs very carefully. Certain layers would share information between the GPUs while others worked independently. It's
Yeah.
almost like having 2 specialized teams working on different parts of a project,
Right.
but coordinating their efforts.
That's so clever. 2 brains are definitely better than 1, especially when you're dealing with a giant neural network. Anything else about this architecture that was key to their success?
There are 2 more things that are really important to understand,
Okay.
and they both relate to that problem of overfitting that we talked about earlier. Remember, this network had 60 million parameters.
Wow.
That's a lot to learn, so overfitting was a major concern.
All right, that whole memorizing the practice test problem.
Yeah.
So how did they keep AlexNet from becoming a one-trick pony?
They used two key strategies. Data augmentation and dropout data augmentation is basically like creating extra study material
Right.
by making slight changes to the existing images. They would generate things like translations, horizontal reflections, and color alterations. This artificially expanded the training data set and exposed the network to more variations of each image.
So instead of seeing the same image over and over, it's seeing different versions of that image, which helps it learn more about the object itself
Right.
and not just the specific pixels in the original photo.
Exactly.
Hmm.
That made the model much better at generalizing to new images. The second strategy, dropout, is a bit more technical. Imagine randomly silencing some of the neurons during training.
Dropout. Okay, that sounds intriguing. What's the point of doing that?
Well, it prevents the network from becoming too reliant on any single neuron. By forcing different parts of the network to work independently, it helps the model learn features that are more robust and generalizable. It's almost like studying with a group of friends.
Okay.
But every now and then, some members of the group are absent, so you have
Yeah.
to learn to rely on different combinations of people or even just yourself to get the information you need.
That's a great way to think about it.
That's a great way to think about it. So by shaking things up during training, they made the network more adaptable and less likely to overfit. All these different elements, the architecture, the ReLUs, the two GPUs, the data augmentation, the dropout, they all work together to create this incredibly powerful model that ended up blowing away the competition.
It really does seem like they thought of everything. But going back to the paper itself,
Sure.
I'm curious, did the authors have any idea what a big deal their work would become? Did they see this explosion of deep learning coming?
Well, it's interesting because in the paper, they actually point out some of the limitations of their model. They say it's still many orders of magnitude smaller than the human visual system, and they talk about how their approach could be applied to video sequences which hadn't really been done before.
So they knew they were just scratching the surface,
Yeah.
that there was so much more potential to unlock.
Exactly. And they even predicted that future progress would rely on faster GPUs and bigger data sets, which, when you think about it, is exactly what happened. We saw huge advancements in GPU technology. Data sets became exponentially larger, and the algorithms themselves became more sophisticated.
It's like they laid the groundwork for everything that came after.
Yeah,
Pretty amazing to think about how far the field has come since then.
it really is. In a way, AlexNet was a proof of concept. It showed the world what was possible with deep learning if you had the right tools and the right resources. And that's what really ignited this incredible wave of research and development that's still going strong today.
So we've talked a lot about the architecture of AlexNet and all the innovations that went into it,
Yeah.
but I'd love to get a little more hands-on. The paper mentions some qualitative evaluation.
Yeah, right.
That was what I'm thinking of, where they basically visualize what the network is learning.
Yeah, exactly. They did some really interesting things with visualizations. One was showing the convolutional kernels that the network learned. Remember those filters we were talking about earlier?
Right.
The ones that scan the image looking for features? They actually showed what those filters look like, and it's fascinating to see how they pick up on things like edges, corners, colors, and even more complex patterns.
It's almost like you can peer into the brain of the network and see what it finds important, what stands out to it.
Yeah.
I remember seeing a visualization where the early layers were learning simple things like lines and blobs.
Yeah.
But as you got deeper into the network, the features became more complex, like parts of faces or even whole objects.
It's amazing how that hierarchy of features emerges naturally from the training process. The network isn't told what to look for.
Yeah.
It discovers those features all on its own just by being exposed to tons of visual data.
That's the power of deep learning, right?
Yeah.
You can learn these representations directly from the data.
Yeah.
Were there any other qualitative evaluations that stood out in the paper?
Yeah, they also looked at the feature activations in the last hidden layer of the network. That layer basically holds a 4096 dimensional vector that represents the network's understanding of an image.
Okay.
And what's really cool is that they compared these vectors for different images to see which images the network considered to be similar.
So images that activate the network in similar ways are also conceptually similar in the eyes of AlexNet.
Exactly. And some of the examples in the paper are mind-blowing. They took an image of a dog and looked for the training images that had the most similar feature vectors. And what they found was that these retrieved images weren't necessarily visually similar to the original dog photo. They weren't the same breed, the same pose, the same background, but they were all clearly images of dogs. It showed that the network had learned to represent the concept of dog at a much deeper level than just pixels.
Wow, so it wasn't just recognizing a particular dog, it was understanding dogness as a whole.
Right, and they did the same thing with other objects like elephants and cars.
Wow.
And in each case, the network was able to pull out images that were semantically similar, even if they looked quite different.
That's incredible. Those qualitative evaluations really highlight how AlexNet was doing something much more profound than just memorizing images.
Yeah.
It was learning to understand the underlying concepts, those visual building blocks.
Yeah.
It's like it was starting to think for itself.
It really is remarkable. And there's one more thing from the paper that I think is worth talking about. They discuss the potential of unsupervised pre-training. Have you heard of that?
I feel like I've come across the term,
Yeah.
but honestly, I'm a little fuzzy on the details. Can you give me a quick refresher?
Of course, unsupervised pre-training is this idea that you can train a network on a large data set without any labels. You're basically letting the network figure out useful features from the data itself before you actually start training it for a specific task.
Ah, got it. So it's like giving the network a general education before sending it off to specialize in a particular field.
That's a great way to put it. And the AlexNet authors thought this could be really important for pushing the field forward, especially as networks and data sets got even larger. They thought it could help the network learn even richer, more robust representations.
And looking back, they were absolutely right. Unsupervised pre-training became a crucial technique for developing these massive deep learning models we see today, the ones powering things like large language models and image generation systems.
Absolutely. It's amazing how much they were able to foresee even back then.
Okay, so I feel like we've covered a lot of ground here. We've explored the architecture of AlexNet, the innovations that made it so successful, and how it's sparked this whole revolution in the field of machine learning.
Yeah, it's been quite a journey.
But before we wrap up this deep dive, is there anything else you think our listeners should know about AlexNet or its lasting impact?
You know, it's funny, when you look back at AlexNet now, it seems almost quaint compared to some of the models that are out there today.
Yeah.
But what's so striking is how much it shifted the trajectory of the whole field. It's like they found this key that unlocked a door to a whole new world of possibilities.
It's really true. I mean, think about all the incredible applications of deep learning that we see today.
Yeah.
Things like self-driving cars, personalized medicine, even art and music generation. It's hard to imagine any of that happening without the groundwork laid by AlexNet.
It's amazing, isn't it? And it just keeps evolving at such a rapid pace.
Yeah.
What's considered state-of-the-art today might be obsolete tomorrow, but that's what makes it so exciting to be working in this field.
It definitely feels like we're still just at the beginning of this journey.
I agree.
And I think that brings up a really interesting question that I'd love to get your thoughts on. As these deep learning models get more and more powerful, as they start to take on tasks that were once considered exclusively human, where do we draw the line? What are the ethical considerations that we need to keep in mind as we develop and deploy these technologies?
That's such an important question, and it's one that we all need to be grappling with. It's not just about the technology itself, it's about how we use it. We need to be really thoughtful about the potential impact of these models, both positive and negative.
Absolutely.
Yeah.
We've seen how powerful deep learning can be,
Yeah.
but we also need to be aware of the potential risks. Things like bias in the data, lack of transparency in how these models work, the potential for misuse. It's a lot to consider.
It is, and it's not just up to the researchers and developers to figure this out.
Hmm.
We need to be having these conversations as a society. We need input from ethicists, policymakers, and the public at large.
Couldn't agree more. It's our collective responsibility to make sure that these technologies are used for good, that they benefit humanity as a whole.
Well said. And I think the story of AlexNet is a great reminder of that. It was a brilliant technical achievement, but its true significance lies in the doors it opened, the possibilities it unleashed. And now it's up to us to decide how we want to walk through those doors and what kind of future we want to build with these incredible tools.
I think that's a perfect note to end on. This deep dive into AlexNet has been fascinating. We've learned about its groundbreaking architecture, its impact on the field of machine learning, and some of the bigger questions it raises about the role of AI in our society.
It's been a pleasure diving into this with you.
And to our listeners, thank you for joining us on this journey. We hope it sparked your curiosity about the world of deep learning and the potential it holds for the future. Until next time, keep exploring, keep learning, and keep diving deep.